Welcome. In this video, we look at section 3.3 and continue our discussion of sets with the topic of proving set properties. Two kinds of proofs that we will look at today: element-wise set proofs and proving new properties from old. Let's begin. So what we want to do in this section is prove facts about sets. What do proofs look like when sets are involved? And we'll use three main tools for our element-wise set proofs. The first is this fact that if A is contained in B, A contained in B, what that means is that if X is in A, then X is in B. When I have intersection, if X is in the intersection of A and B, that means that X is in A and X is in B. And if I have X in the union of A and B, that means X is in A or X is in B. So we go from statements that have to do with sets and we turn them into some logic statements. To prove that one set is contained in another, here's the typical path that we follow. We let X be an element of the first set, S, and then we prove that X is in T. If I can do that, if I can prove that for every X in S, X also happens to be in T, then that shows set containment. That will show that S is contained in T. This is where the element-wise comes in from element-wise set proofs, because we focus on an element and we see where that element lives. Okay, let's see some examples. Example 1. Here's a claim. For all sets A and B, A intersect B is contained in A. Now, let's just draw a little Venn diagram and see if that seems reasonable. There's sets A and B, and here's the intersection, A intersect B. And it looks like, yes indeed, A intersect B is contained in A. But let's prove it rigorously. Now, to start, the first line is going to be, let sets A and B be given. And let me think about the very last line. Where will we end up? Since every element of A intersect B is necessarily in A, this shows that A intersect B is contained in A. So I want to show that if I take an element in A intersect B, then that element will have to also end up in A. Okay, so now let's actually do the proof. We'll dig into the elements. Let X be an element of A intersect B. This means X is in A and X is in B. Oh, so in particular, therefore, X is in A. So I started off saying X was in A intersect B, and I ended up showing that X was in A. Since every element of A intersect B is necessarily in A, this shows that A intersect B is contained in A. Very good. Example 2. Claim. For all sets A and B, if A is contained in B, then A is contained in A intersect B. One thing that's a little bit different about this claim is that it has a little extra hypothesis. Again, let's look at the Venn diagram and see if it makes sense. So if A is contained in B, here's A, there's B, then A is contained in A intersect B. Well, it seems as though A intersect B would just have to be A itself. But at any rate, it seems true. A is contained in A intersect B. What does the proof look like? The first line, let sets A and B be given such that A is contained in B. What will the last line look like? Since every element of A is in A intersect B, this shows the containment. Now let's dig into the elements. Where will I start? What do you think the first line will be? Do you know? Let X be an element of A. That's the A right there that I'm interested in. I'm letting X be an element of A, and I want to show that X is an element of A intersect B. Well, I can use the hypothesis. A is contained in B, so this implies that X is an element of B. Since X is in A and X is in B, X is in A, X is in B, then X is in A intersect B. So I started off by saying X was in A, and I ended up showing that X was in A intersect B. So that shows the containment that I want. Okay, time for you to practice. Give this thing a try, pause the video, and when you are ready to check your work, start it up again. Let's take a look. Proof. So we start off with the hypothesis. A, B, and C are given such that A is contained in B and B is contained in C. Let X be an element of A. Well, since A is contained in B, we find that X is an element of B. And also, B is contained in C. Therefore, it has to be that X is in C. This is exactly what containment means. I started off by saying X was in A. I ended up showing that X was in C. Since every element of A is necessarily in C, this shows that A is contained in C. Incidentally, just as a by the way, this is something called a transitive property. We see the transitive property throughout mathematics. If A is contained in B, B is contained in C, then A is contained in C. Another example would be with real numbers. If A is less than B and B is less than C, then A is less than C. So there you go. You got a fancy word for that. Set equality. What if I want to show not just containment, but I want to show that two sets are actually equal to each other? Well, it just boils down to two separate proofs of containment. To prove that S equals T, we prove that S is contained in T and T is contained in S. And then if I can do those two proofs, I will show equality. So you may not have noticed it, but we've actually shown containment in two different directions. The first proof that we did showed that A intersect B was contained in A. The second proof that we did said that, well, under certain conditions, A was contained in A intersect B. So we could put those together and say, if A is contained in B, then A intersect B equals A. So we've done the two containment proofs in the two different directions. Algebraic properties of sets. Sometimes it's nice to have identities that help us simplify expressions. And the same is true with numbers and algebra, as it is also true with sets. For example, theorem, for all sets A and B, A intersect A union B equals A. This is sort of a simplifying rule. If I ever come across the situation where I have this kind of expression, I can simplify it into just A. So to prove this kind of property, it's an equality, so I need to prove containment in both directions. And you can see here's the claim 1 that I need to show and claim 2. These are pretty easy. I'll do claim 1 and I'll leave claim 2 for you. How is claim 1 going to work? Let X be an element of A intersect A union B. Then what does that really mean? Then X is in A and X is an element of A union B. Oh, but in particular, X is an element of A. There we go. So that wasn't so hard. X was in the intersection of the two, therefore it's in the first, so we have that containment. So just a little sketch of the proof there. See if you can do something similar. I think it's maybe a couple lines longer, but maybe you could prove the claim 2. And when you've done that, you've proven this nice algebraic simplifying property. And by the way, this is called the absorption property of sets. There are lots of other rules. It turns out, take a look at these. Properties of set operations. Lots of ways that we can simplify combinations of sets. Maybe even pause the video for a second and just sort of look over these for a little bit. Look at the names, look at the two different columns. Why are there two different columns? Think about how intersection and union relate to each other. And then, when you've had enough of looking at that, I want to draw a couple of these in particular to your attention. The distributive property is used a lot. Look at this. A intersect B union C is A intersect B union A intersect C. We might say that I can distribute intersection across union. That's a little bit like when I distribute multiplication across addition. So A times B plus C is A times B plus A times C. I can distribute multiplication across addition. So I can also distribute intersection across a union. But curiously, look at this. I can also do the distribution with union. I can distribute union across intersection. And we don't have that in algebra. Not in algebra. I can't distribute addition across multiplication. So that's kind of a curious fact of the distributive property with sets. that it works both ways with intersection and union. Another good set property to consider is identity. A intersect the universe is A union the empty set is A. And another one that comes up a lot is De Morgan's laws. The complement of A intersect B is A complement union B complement. That is a lot like something we saw in logic, also called De Morgan's laws, coincidentally. How did it go? In logic, we had something like not P and Q is logically equivalent to not P or not Q. And we also had the other part in De Morgan's laws, not P or Q is logically equivalent to not P and not Q. So there are some really interesting tie-ins that are coming about here with sets and logic. Let's prove a set identity using some of those properties. Here's the claim. For all sets A and B, A intersect B complement intersect A complement equals A intersect B. All right. So maybe the first thing I might do is say, well, this complement on the outside applies to the intersection of two things. Let's bring that complement in, and I'll change that to union. That was the De Morgan property. And then maybe after that, I'll say, oh, well, you know what? That B complement, that's really the same thing as B. What property was that? That was the double negative property. After this, maybe, I don't know, I'll distribute the A. So that becomes A intersect B union A intersect A complement. That is the distribution property. And then what? What have I done here? Well, it looks like I've combined the A intersect A prime, and that property is the negation. And then finally, oh yeah, when I union something with the empty set, that's just the same thing as the original set. And what was that property called? That was the identity property. So I've been able to turn this expression with sets into a much simpler one. And it's set equality. So I could have done this with an element-wise proof, saying let x be an element of the left-hand side, and then showing it's an element of the right, and then saying, no, now let x be an element of the right-hand side, and show, okay, it's an element of the left. But instead, taking this sort of broader view with set properties, I'm able to do equality, 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 all the way down, and end up with the statement I want. So it's an interesting, different way of looking at these set proofs. All right, this is example 2, but let me ask you actually to pause the video and give this a try, and then start up the video again when you want to check your work. Okay, go to it. All right, and the answers are distributive, negation, commutative, and identity. Okay, so we've covered a lot, element-wise proofs and proofs using set properties, and so I will stop here.